pull my bias. Actually, has to go negative. Lower that down. And maybe make this a bit wider. There we go. So there's my collision object. And now when I hit play, we'll see this collision object actually recomputing itself as the object moves down, and the divergence projection trying to avoid having the collision object move through. But the object, you can see the fluid is still moving through the collision object though. This is because the solver is assuming that the velocities inside the collision object are the collision object's velocities. And so when the fluid extrapolates its velocities into the collision object, that just sort of cements that it should actually collide through. Actually, the other reason why it's colliding through is because I haven't set the collision field parameter. So I'll set the collision field parameter first. And now we'll see it again also go through, but not as much as the time you just saw previously there. There we go. So I'll just turn off the orange because that's sort of getting in the way here. So you can see, and probably be useful to get rid of the velocity as well. So you can see those blue particles have definitely gone through, and I don't know if any of the pink particles, yeah, some of the pink particles have also gone through. So for the reason I explained earlier, what we want to do is zero out the velocity inside that collision object. And for this, there's the gas and force boundary. And I can put that in and tell it to zero out the velocity field wherever the collision field is present. And now we'll have it go through and avoid penetration. I can actually still penetrate a bit here because it's going to do a step of the particles based on the velocity field, so it could overshoot and end up in the object. Normally we'd have a particle-based collision method to stop that, but we don't in this case. It's just purely the velocity field causing the collisions. So there we have the result. And I'll turn off the collision geometry. And we're going to see these two little lobes. Because they got different constant forces, they effectively get different gravities, so they're falling in two different directions. So we get this sort of two-lobe effect. And so that shows how to build a flip fluid solver and how to build a smoke solver. So thank you very much for listening on this, and now is the time for questions and discussions. And so the question was that when I switched from the pick to the flip, I pointed out this let the particles maintain their own individual behavior. But then the question was, in this case, these particles seem to have very boring behavior. They're all going up or all going down. So why did we suddenly see splashiness in the resultant sim? The answer is because inside a cell, the group of particles inside a cell had interesting behavior that's different than the particles around them. And so some particles were going up and some were going down. And to the pure pick method, those will all be assigned the exact same consistent behavior. But the flip allows them to remain inconsistent, some going up and some going down, which then percolates and causes much more erratic behavior downstream.
But wouldn't that get erased?
Well, thank you very much for coming, and